Hello, Drew. Okay, so let's continue with our discussion on these two types of equivalent circuits, the Thevenin and Norton equivalent circuit. As you recall, the Thevenin equivalent circuit is essentially a voltage source in series with a resistor. So essentially what we're doing is we are representing a complex network using a simple two-port system. So we can call this, port A or B or whatever names you want to assign them. The two important pieces of information here are that we call this source voltage, the Thevenin voltage, and the source resistor as the Thevenin resistor. Now we can find these quantities by first determining the open source voltage. So open source voltage, whatever that comes out to be, is going to be your V Thevenin. Similarly, we will find the I short circuit, and that I short circuit and the V Thevenin can help you find the R Thevenin. Okay, but that's not a unique way of finding the resistance, the Thevenin resistance. And we mentioned that there are other techniques. So you can use starting from the equivalent resistance option. And if there are sources, of course, there will be sources in the circuit. So the sources could be removed by shorting out your voltage sources and open circuit replacement of a current source, and then you can find equivalent resistance. And also, of course, you have the delta and Y models of resistances, so which helps you find any quantity. So when you can interchangeably translate between delta and Y circuits, if you find that none of the resistors are in series or parallel. Okay, so once you convert it from one form to the other, of course, then you will have a starting point, and then you can further simplify your circuit. You still will be using your KCL, your KVL, your node voltage, mesh current, current division, and voltage division. So I mean, all these techniques that we have covered so far in this course will all be applicable wherever possible. In addition to these open circuit voltage, short circuit current, and R Thevenin that you can find using by turning off, as I mentioned, the voltage source and the current sources. So all these techniques are available to you. But the bottom line is you need to bring the circuit to this form, which is, of course, a simplified representation of a complex circuit. So this is the Thevenin equivalent circuit. And if you were to represent it by a Norton equivalent circuit, that would be this form. So let's say we still have these ports A and B, R Norton and I Norton. Okay. So just like in the Thevenin model, when we talked about the open circuit voltage that was equal to the Thevenin voltage, in this case of the Norton equivalent circuit, if you attach a short to this and you're finding the I short circuit, so if you, as you can observe that this short will take out the Norton resistance out of the picture, which means that I short circuit would be equal to I Norton, right? So that's one parameter. And then you will find the open circuit voltage and using these two quantities you can then determine the Rn. So considering some of the quantities are unknown, right? So in this case we will find Rn which is going to be V open circuit or either IN or I short circuit. They're both the same quantity. So these are the basic techniques that we're using. Okay. So now let's look at some examples after the summary. Okay. So we're given a circuit. We'll start with a simple example and then we move to more complex examples from this point. So it is represented by a two-port network. So there's two ports here. There's a 10 kilo ohm resistor here and 15 kilo ohm resistor here. We have a 12 volt source voltage and we're asked to find okay, so we need to find the equivalent circuit for this. And we start with our, the standard technique, which is finding the I short circuit and V open circuit. Okay. So if I were to find the open circuit voltage for this, so this voltage would be the same voltage that is across the 15 kilo ohm resistor, right? So because, voltages in parallel are identical. So, and if we find the voltage of the 15 kilo ohm resistor, we should be fine. So I have a 12 volt source, and then I have two resistors. So if I were to find the using the voltage division technique, I can find the VOC. So essentially VOC can be applied to the 15 kilo ohm resistor. So we can then say that the source voltage times the 15 kilo ohm resistor. So let's just label them as this, and then the equivalent resistance would be this, right? So applying this, the numbers, we have 12 volt here, and we have 15 kilo ohms, and then we have 10 plus 15 kilo ohms. So what we get is, this is also kilo ohms. So we get 27 25 at the denominator, and we have 12 times 15 is 180. Or 25. So let's do the calculation there. So that's 7.2 volts here. Okay, because it's voltage here. So the V open circuit is 7.2 volts. Now we need to find the I short circuit. So to do that, we will have to connect a short circuit and find the I short circuit here. We have 15 kilo ohm resistor here and 10 kilo ohm resistor here with a 12 volt source. So now for the short circuit, it will basically bypass this 15 kilo ohm resistor. So that resistor would be shorted out. So the only resistance that you have now is the 10 kilo ohm, right? So the path is going to be 12 volt source to the 10 kilo ohm, and then that short circuit there. So essentially we can find this I short circuit value by V over R. So V in this case is 12 volts and R is 10 kilo ohms, right? Because we have bypassed this. So what we're going to be left with is 1.2 milliampere. Okay, because we have this K in the denominator, which is going to make this milli. So now I short circuit has become 1.2 milliampere. Okay. Now remember that we need to represent the Thevenin equivalent circuit using a voltage source and a resistor. Okay, the resistor is called R Thevenin and the voltage source is V open circuit or the V Thevenin. So which we know, we found the open circuit voltage to be 7.2 volts. But now I need to find the R Thevenin. So remember, R Thevenin is equal to V open circuit or I short circuit. So the value for that is 7.2 volts or 1.2 milliampere. So this becomes 6, and the milli would make this kilo ohms, and volt over amp is ohms, and the milli when transferred is going to become kilo. So now we have 6 kilo ohm for the R Thevenin. Okay, so that is your equivalent circuit, and that's the standard technique. The standard technique is finding these two quantities, and these two quantities are going to give you this quantity, and that can be represented here. Okay, so that's just a standard format. Okay, so let's take a look at one more example. Any questions about this one? Okay,
I'm just trying to keep up.
okay. Okay, so for the next example, we're asked to find the Thevenin equivalent and Norton equivalent circuits. So this time we need to find both. And all there is, once you find one of them, you can use source transformation to convert it to the other. So they are interchangeable between the two. And it is saying find the Thevenin equivalent and Norton equivalent circuits seen by the load. Okay, so once you see the circuit, you'll see what it means. So there's some load resistance there. And for the part, this is the first part of the question. The second part is saying, so this time we have a value for that load, which is 50 ohms, right? So let's write this circuit here. So we have so here we are drawing the circuit, and this is the load. So now what we're saying, of course, there'll be some current passing through it also. So what we're saying is from this point, how does the circuit look like, right? In terms of a Thevenin equivalent and a Norton equivalent. So let's place the values there also. So we have a 20 ohm resistor here, another 20 ohm resistor here, a 40 ohm resistor. This is a 50 volt source, 30 ohms and 60 ohms. So these are all the values of the various components within this circuit. Okay. So let's think it through. You know, what would be the best approach? Where should we start from here, right? So if I look at the right-hand side, after I sort of disconnect this load from my circuit, so I probably right-hand side is not the best choice, because if you see on the left-hand side, you have two resistors in series, and this series combination of two 20 ohm resistors is in parallel with a 40 ohm resistor, right? So once you have that, that means that you will have that combination, that parallel combination would be in series with a 50 volt source. So that sort of brings the right-hand side to a more standard form that we're used to, where we see that there's a source, some source voltage is, you know, on the right-hand side, and then there is some rest of the circuit like that, right? So we want to bring it to that form so that it's a little bit consistent with what we're used to, okay? So the first thing we want to do is we want to combine the two resistors. So, and what I will do is I'll basically redraw this circuit each time I modify it, okay? And on the right-hand side, what I will do is I'll do any analysis or any combinations that takes place. So in this case, it's pretty straightforward combination of two resistors that were in series, which are now in parallel with the 40 ohm resistor, and we have this 50 volt source, and let's consider the rest of the circuit. Okay. Okay, so now we have two 40 ohm resistors that are in parallel to one another. So let's do the equivalent. Okay, so we can take the common denominator is easy here because you could see that both denominators are 40, so I can take this as common, and then I can add the numerators, which are going to be 1 plus 1. Okay, so now this is equal to 1 over R equivalent is 2 over 40. I do the cross multiplication. I get 2 R equivalent is equal to 40. And then R equivalent is 40 divided by 2. So what I did was divide both hand side by 2. So I get rid of the 2 on the left hand side of the equation, and this is going to give me 20 ohms, which is consistent with what we have discussed in the past when we were talking about the equivalent resistances, that whenever you have two resistors of the same quantity connected in parallel, the equivalent value of those two resistors of the same value would be half of that value, right? So if I have two 10 ohm resistors connected in parallel to one another, the equivalent value of those two is going to be 5 ohms. Similarly, in this case, we have two 40 ohm resistors, and by this calculation, we also ended up with a 20 ohm equivalent value. Okay, so let's go ahead and redraw this with this 20 ohm resistor. Okay, so now in a more standard form, we can redraw this circuit in this way, where we have a 20 ohm, 30 ohms, and 60 ohm resistors. And over here, I have this load here, which is voltage there. So now, if I look at this, there are two ways I can go about this, right? One is I see a Y circuit here. So I can convert this to a delta combination, or then I'll see what I'm left with. But again, that's one way of going about this process. So the other way is if we apply source transformation, which is a relatively easier technique in my opinion. So if we apply source transformation, we can convert this voltage source to a current source. And the way it can help me is just the thought process behind that is that the 20 ohm and 30 ohm resistors would become a parallel combination if I do that, right? So if I do that, it becomes parallel combination, I combine them, and then what I will have is a current source in parallel to the resistor, and I can go back and convert this to the voltage source by doing source transformation one more time. And what this will do is then whatever the equivalent value of the 20 and 30 ohm resistors is, will become in series with a 60 ohm resistor, right? So that's the thought process behind this change. So let's go ahead and go through this. Again, that's not a unique way. I mean, the other ways you can find the equivalent circuit. Okay, so based on the polarity that is given, so of course, when I'm converting the current source, the voltage source or current source, the arrow would always be pointed to the positive direction, right? So of the positive terminal of the voltage source that we are converting from. So in this case, that's what we get, and this resistor becomes a parallel combination. So this is 20 ohms, this is 30 ohms, and then I have the 60 ohms here. And this is my two-port network with a load connected like this. Okay. So let's find these values. Okay. So what is my current? My current is V over R. So the V was 50 volts. And this is the source current that I'm trying to find. And this is 20 ohms. So when you look at this, this is, you know, if you do the division of 50 divided by 20, that is 2.5 amperes. Okay, so that is what the magnitude of this current source is, 2.5 amperes. Okay. The next step that I want to go through is combining these two resistors that are connected in parallel, right? So this is 1 over R equivalent is equal to this one we know is 60 ohms, 1 over 20 plus 1 over 30. So whatever technique you feel comfortable with, you can choose that. For example, you can say that I can go ahead and do 1 over 20, which is going to be 0.05, and 1 over 30, which is going to be 0.0334, and then I can add them and do the cross multiplication and find the equivalent resistance value. That's one technique. The other technique is the common denominator. So I'll just kind of show you both. If I do the common denominator, what I will have is 60 is the common denominator here, okay, which is divisible by both. So that's the smallest value that is divisible equally by both the denominators, right? So you can find that. So this is 60 is the smallest value that is divisible by both of these. And this is going to be 3. So 3 times 20 is 60, plus 2 times 30 is 60. So I will end up with 1 over R equivalent is equal to 5 over 60, which is by cross multiplication equal to 5. R equivalent is equal to 60. And then dividing both hand side by 5, R equivalent is equal to 60 divided by 5 is equal to 12 ohms. If I went through this technique, this is the process. If I go through the other process, which is the, you know, the fractional values, so that's going to be 0.05, which is the result from 1 divided by 20. 1 divided by 30 is 0.034, right? So then we can say, by the way, this is separate. So 1 over R equivalent is 0.084. Okay. Now I can do cross multiplication because, of course, there is a denominator of 1. So if we do the cross multiplication here, we are going to have 0.084. By the way, this is our equivalent is there, is equal to 1, and our equivalent is equal to 1 divided by 0.084. And we can find the value of our equivalent. So this comes out to be 11.9, because of course the reason you will not have the exact value is because we use 3 significant figures to write a decimal point, right? So we truncated that long value and took the exact, not the exact value. So again, it's approximately 12 ohms is what we can say. So this is now, we use this as 12 ohms here. Okay, so now this is what we get. Now the next step in this process is to convert this back to a voltage source using the source transformation. Remember, the goal is to find the easiest possible or the most comfortable. I mean, there's not as I mentioned, there's no unique solution for it. It is, you can get to the right solution using different techniques. I wouldn't actually go through the solution of it, but I can show you how other techniques can be used here. So in this case, my voltage is current time resistance, right? So the current is 2.5 and resistance is 12 ohms. So that becomes 30 volts. So I can write this as 30 volts. Okay. And here I have the 12 ohm and 60 ohms, right? So the original question was, from the point of view of the load, what is the equivalent circuit in terms of the Thevenin equivalent and also the Norton equivalent? So now we are at that point where we have reduced it into, so since these two resistors are in series, so we can write this as a single resistance, which is 12 plus 60, so that is 72 ohms. And this one voltage source is going to be 30 volts. Okay. Now, in terms of the voltage that is seen by the load, I mean, you can consider it's a negative voltage there, right? Because it's the polarities are opposite. So, so essentially, you can then say that this is what the Thevenin equivalent circuit is. And if we convert this to Norton, all you have to do is to apply the source transformation. And this time, this will still be 72 ohms. And the current is I is equal to V over R. So it's 30 divided by 72. And let's find this value. So I will get 0.416, say it's basically 0.4166 amperes, or this could be approximated to 417 milliamperes. So both answers would be correct. Okay, so this. Okay, so now this is the Norton model. Okay, so that takes care of the first part of the problem, right? So this time we sort of didn't follow the short circuit and open circuit technique, but if you were to do use that technique, you still can use it. But in my opinion, it will be a little bit more because you will have to bring the circuit to at least this form, and then be able to apply the I short circuit and V open circuit. And you could use the node voltage technique, or you could use the mesh current technique to find these quantities. So for that, I felt like that's more of a lengthier process. And I felt like if I were to resolve the circuit by source transformation, that would be a lot easier. And that's why I chose this technique. But if you use the mesh current or node voltage technique, you can still end up at the same result. The goal is to find the open circuit voltage and the short circuit current. And that can be determined using those two techniques. So once you have those two values, the open circuit voltage would be equal to your Thevenin voltage. And using the I short circuit and the Thevenin voltage, you can find the Thevenin resistance and, describe your equivalent circuit using those two quantities. Okay, so those are the different techniques that you could use. But if you were to use like this one essentially is in a short circuit. Let me just show you this. Okay, so let's say if you were to find I short circuit, you place the short circuit there, right? So here you have 20 ohms, you have 30 ohms, you have 60 ohms, and you would write the equations for the two meshes there, right? But this mesh, so this one could be I1, and remember there's a I short circuit. So this is I2. So when you solve for I2 and I1, the I2 would be equal to I short circuit. So that'll be one quantity that you can find using this technique. The other one is through node voltage analysis, right? So let's look at how many independent nodes do we have here, right? So the independent nodes that we have is this particular node here, and then we can find the open the open, so this load where load is connected, that will be the open circuit there, right? So based on that, we can do the KVL, essentially the KCL at that node, and we can find these currents. So once we do find those currents, at that point, then you can find the V open circuit. And you have the I short circuit there, and based on those two relationships, you can find the Thevenin resistance. But my preferred technique would be for this particular problem is the source transformation method. Okay.
The first method, the very last step, I guess I should say the second to last step, you had 30 volts,
yes,
and 72 ohms in series.
Yes.
why did we go to the next step? Why didn't we just leave it at like the load resistance is 72 ohms at 30 volts? How come you took it
Okay.
to another step and put that ohm resistance and in parallel?
Yeah. Yeah. So basically, let's look at the original question. The original question was to find not only Thevenin equivalent, but also the Norton equivalent, right? The Norton equivalent is the current source in parallel with the resistor, right? So they both could be interchangeably used using source transformation. So since in the first problem, if you look at this first question, I only determined this circuit and I left it at that, because the question was asking me to simply find the Thevenin equivalent model, which is the voltage source in series with the resistor. But in this case, I'm being asked to not only find the Thevenin equivalent, but also the Norton equivalent, right? So essentially, this is also, so this is part of the, so this is for the Thevenin equivalent circuit, and the other one, the circuit to the right, is the Norton equivalent circuit, just based on the question that was asked.
Okay, that answers my question. I wasn't sure if. Yeah. So there's two answers, and it's the last two. I get it.
Correct. That's right. Yeah. So that's the reason I went to one extra step. Now, if you look at the statement of this problem, there's a part B also, right? So part B is saying that find the voltage, current, and power delivered to a 50 ohm load. So far we've been just assigning the load as a box with L inside, but now we will have to actually assign a value. But the good news is that we already have equivalent circuits, right? So if I use the Thevenin, for example, so if I use the Thevenin equivalent circuit, I have this model here, and to this port, I just connect this RL and RL value is 50 ohms, right? So we're being asked that what is the current, and I'll just write it here. By the way, let me just make some space. So this is the current. The voltage and the power, right? So we need to find those quantities. So if I were to find the current, that is, okay, so that's my formula. For the voltage, you can you can find this using the KVL. You can also use the current division. I'm sorry, voltage division to find this voltage. So both of these techniques would be fine. So I'm just going to use the voltage division here because I know all the quantities here. So the source voltage times the resistance, the load resistance, times the equivalent resistor. So that is going to be the formula there, right? So I can find this voltage pretty easily. So once I have that, the source voltage, as you can see, the negative terminal is at the top this time, right? Which means it's a negative voltage seen by this point here, right? At this node, we would see a negative voltage. So therefore, we will say it is minus 30 volts times the load resistor is 50 ohms, and the equivalent resistance is 50 plus 72. okay? And then you can do the math here. So here I have 1500. If I take the product of these two, and if I take the product of, or the sum of these two, that is going to be 122. And don't forget the negative sign there, just like I have. So let's go ahead and do the arithmetic there. So we have
We got negative 12.3.
negative 12.3. Okay, so that is my voltage here, right? So that is my, the voltage is one quantity is known now. Now, the current through that resistor is, of course, the voltage over the resistance through that, through that resistor. So therefore, now I have the voltage, so I can then find the current also. So the voltage is negative quantity here. So it's minus 12.3. And the resistance is 50. So let's do this one as well.
Negative 0.246.
246. Okay. So now this is my current. Okay. This is my current. This is my voltage. And the third quantity that I'm asked to find is the power, right? So if I have these two quantities, I can do the power also. So P is equal to IV, and I is minus 0.246. The voltage is minus 12.3. And if I do the calculation there, I should have my power value.
Three.
Okay.
This is going to be watts.
Yeah, 3 watts, right? So we have 3 watts as the power. So that takes care of our part B of the question, right? So in this way, we found the equivalent models. And we also, once we do that, we can do analysis on the load, and we determine, the current, voltage, and also the power for that is delivered to the load from this equivalent model. Okay, so that's this example. Let's look at one more example here. Okay, so we're given some circuit where we are asked to find the Thevenin equivalent to the left of the load, just like we did before. And there's a part B also. Okay, so for part B, using the Thevenin equivalent circuit, there's a 10 kilo ohm resistor that we need to find the power for. Okay, so let's go ahead and go through the first process, and let's draw the circuit here. So again, we're looking from the point of view of the load. So everything to the left of the load needs to be represented as an equivalent circuit. So let's assign these values. So the source voltage is 15 volts connected with the 3 kilo ohm resistor, then the 6 kilo ohm resistor, 2 milliamps, current source, 4 kilo ohm resistor, and a 3 kilo ohm resistor on the top. Okay. Again, you have the option to use any of the techniques that are available to you. If I look at this circuit, you know, I could sort of spot that if I use the source transformation on the voltage source, what that will do for me is it will convert this current source to this voltage source into a current source, and then I have two current sources in parallel. I can combine them. That's one approach to that. The second approach is that I have a 2 milliampere current source connected in parallel with a 6 kilo ohm resistor. So I can also convert that one to a you know, voltage source. So once I do that, essentially, I will have two voltage sources connected in series, and then I have all these resistors connected in series. So I can combine the resistors and I can combine the voltage source. So that's probably a shortcut if I look at it. But either technique you use will take you to the same end result. The other process is if you go through the other you know, techniques, which are the node voltage analysis. When we do the node voltage analysis, you will identify the node that is going to be you know, your independent node. You use your reference nodes and do the KCL at the nodes and find the unknown quantities there. In this case, in the unknown quantities will be your open circuit voltage and the short circuit current, right? So those could be determined. But again, my preferred technique, which is least prone to any mistakes and a rather shortcut, is the source transformation technique, because the other processes are quite lengthy, right? For each of these processes, you'll be using essentially you know, the series of equations, and then you'll have to solve those equations. So it's going to be a pretty you know, lengthy analysis. So instead, what I will do is I will combine, rather I will apply the source transformation on this current source. But if you can spot that and you go through by converting the 15 volt source to a current source and the source transformation, that is also fine. It just adds one additional step where you would combine the two resistors in parallel together and then bring it back to the voltage source by applying another step of source transformation. Okay, so if we go through this technique here, I still have my 15 volt source connected to 3 kilo ohm resistor, and in this case I have my this current source can now be converted to a voltage source connected in series with this 6 kilo ohm resistor, And don't forget this 4 kilo ohm resistor. So this is the 3 kilo ohm resistor here, 6 kilo ohm here. And let's find what is the value of this this voltage source. So the voltage source is V is equal to IR, right? So this would be I is 2 milliampere and resistance is 6 kilo ohms. So combining the two, you're going to have 12 volt because the kilo and milli are going to cancel each other out. So you're going to be left with a 12 volt source here. Okay. So now we can combine these two sources since voltage sources in series can be combined together to find equivalent voltage. And similarly, the resistors in series, so we have 4 resistors in series that can also be combined together, right? So, so you can use this process to find this these quantities here. Okay, so let's go ahead and do that. So I get 3 volt from there, and then I get 16 kilo ohms if I combine everything. In fact, actually, you know what? The issue with that is that so we're looking at it from an open circuit point of view. Okay, so from the load perspective, yeah, this is what we're gonna get. Right? I was thinking, I thought it would be open circuit, but it's not open circuit. There's a load connected there. Load could be a short circuit or any quantity there. Okay, so you have the 3 volt and 16 kilo ohm resistance, and once we have that, then essentially you can determine. So that's my Thevenin equivalent, which is the part 1 of the question. The second part was to find the current and power if the load was a 10 kilo ohm resistor, right? So it'll be the same process. So we need to find the current and we need to find the voltage there. Okay, so this voltage, and using our technique of voltage division, we can find this to be, so let's say if this is R10 kilo ohm, and then you can add the two. Okay, so Vs is 3 volts. This is 10 kilo ohm. And we have 10 kilo ohm plus 16. 30 divided by 26. So we have 1.15 volts there. Okay, so V is equal to 1.15 volts. Okay, so once we have that, we can then find the power, because remember, power P is equal to IV and I is equal to V over R. So we can say V squared over R is what the formula for power is. So V square is 1.15 squared divided by 10 kilo ohms. And that's what, so could you do the calculation for 1.15 squared divided by 10 kilo ohm?
That's 0.13225.
Okay, so it's 0.13
225.
225. Okay.
I'll do it again. 1.15 divided by 10. Yeah, 0.13225.
Okay, so then, and this is milliwatts, by the way, because there's a kilo ohm here, so then that will convert it to a milliwatt. So this is the power delivered here. Okay, so over here, what we did was, took this the encircled area, converted it into a series combination of voltage source and in series with the resistor. And then since the polarities were opposite of the two voltage sources, therefore we took the difference of the two, which is 15 minus 12, so that's 3 volts, and then combined all the resistors and found the equivalent circuit. In the same way, then we did the power and voltage calculation. So the voltage across that 10 kilo ohm resistor was determined, and using that we then found the power. Okay, so I mean, source transformation could be very helpful in this analysis, which can reduce a lot of steps for you, because what it does, it takes a series resistor, bring it to parallel, and similarly it takes a parallel resistor in a resistor in parallel to a current source and bring it to series. So using this, you can combine a lot of resistances, a lot of sources, it could be current or voltages, and combine them together to simplify it. So step by step, you go through that process and find a simpler circuit. But again, as I mentioned before, it shouldn't hold you from using any other technique like the current division, the voltage division, the node voltage analysis, mesh current analysis. But I personally prefer this technique here. So again, that's just up to your choice. Whatever you feel comfortable with, you can go through that process. So this pretty much are all the examples I wanted to show you for this topic. The next topic, I don't think we have sufficient time to sort of get into it, but before the break, we will maybe touch up on a couple of topics, at least one, and we'll do it on Thursday. Okay. So are there any questions about any of the examples that we've covered so far in this lecture?
No, this has been great. There's just a lot of opportunity to make a mistake, like subtracting the voltages because they're pointing towards each other, or kiloohms and it's not milliwatts or whatever.
Right,
So
right.
there's a lot of you mess up this tiny thing at the beginning and it just
Yeah,
compounds the problem. So
right. Right. And I agree with you. It's a snowball effect there that,
yeah,
you know,
it's super easy to follow along with, and you make it seem so easy, but yeah, when you're left to your own self, you're But
it's
I appreciate it. This has been great. This has been a good explanation.
okay, great. I'm glad you found it useful. What I will do is I will assign a homework assignment on this topic, and it will be an opportunity for you to get some more practice. And based on that, and of course, we can have a discussion about it also in the next lecture, or the lecture following the break. But basically, what I'll try to do is I'll maybe post it today so that you have a time to look at it between now and the next lecture. In case we don't have a chance, I'll provide sufficient amount of time so that you can complete and have some time to look at it. And also we can discuss offline if you have questions. So you can always reach out to me through email or the text messaging system that the CTU messenger. So that would be fine also. So in fact, in the CTU messenger you can attach your screenshots, and that way I can review your work. So that way, if you have any questions over the break, when basically we won't be having after the Thursday session, we will not have sessions for a week, the following week, the Christmas week. So then we'll come back after basically the new year. So there'll be some sort of downtime, but we can use the opportunity of the communication techniques to if there are any questions. Okay, so I'll conclude the session now, and I'll see you on Thursday then.
Okay, sounds good. Thank you.
Thank you for your time.